All right, so ladies and gentlemen, we have 3 more laws to talk about in gases. The first one we mentioned briefly in the lab, and that's the ideal gas law, sometimes called PIV-NERD. So most of you figured out notes, paper, calculator would be good, because when we learn the laws, then we're going to do practice with the laws. And that's the ideal gas law, PV equals nRT. I actually knew a chemistry teacher who had that on his license plate. I'm not exaggerating. He's the one that showed me some really slick reactions that we did in class from Ashland, Oregon. Anyway, so PV equals nRT. It's all the reactions, all the laws we've done so far, the combined law, Charles' law, Lusak's law, and Boyle's law, were about gas changes. Well, PIV-NERD is just the quantity of a gas and the pressure and volume and temperature it exerts when you have a certain amount of gas. So difference between the combined law and PIV-NERD is you have an N in there. So this will tell you, based on the number of moles you have, what the pressure, volume, and temperature will be. Now in this class, we're almost always going to use atmospheres for pressure. And when you use atmospheres for pressure, your R is 0.0821. That's not technically the standard gas constant. Technically, the standard gas constant is 8.314 when you use kilopascals, or 8,314 when you use pascals. But in this class, we will almost always use atmospheres. So R will almost always be 0.0821. I can't even think of a time where we're going to use any pascals in our calculations from here on out. But just realize that R value could change if you're doing tutorials on the internet, and you have a situation where your pressure is in pascals, then your R is going to be 8,314. But here, if pressure is atmospheres, 0.0821. Okay, any questions before we jump right in? All right, so got lots of practice today. So using the ideal gas law, consider this. What volume does 3.4 moles of helium occupy at 1.2 atmospheres and 300 Kelvin? So what we would do, as always, is write our formula down. EV equals nRT PIV-NERD. PIV-NERD. So in this exercise, what's my pressure? 1.2 atmospheres. And do I have a volume? Nope, volume is what I'm looking for. Do I have an N? 3.4 moles. 3.4 moles of heat. Do I have an R? 0.0821. And do I have a temperature? 300 Kelvin. Okay. Then it just becomes arithmetic. Just solving for the variable we don't have. And again, like I always say, you got an equal sign sitting in the middle of your equation, check your work. You got an equal sign sitting in the middle of the equation, check your work. And don't give me the answer, I'm going to ask for a vote. Your favorite mathematics technique to get V all by itself. Then give me a thumbs up when you've got an answer that you like. Okay. About half the class. Take about 30 more seconds. Okay, if you got a number larger than 10, raise your hand. Good. Larger than 20? Good. Larger than 40? Larger than 80? Ah, good. What'd you get? 69.7. Can I turn that up to 70?
Yeah.
All right. So basically, what we're saying is if you have 3.4 moles of gas at 1.2 atmospheres and 300 Kelvin, it will occupy a volume of 70 liters. Make sense?
How do you know if it's like liters or no liters?
It's good. Liters is our standard unit for Pivner, so we're going to use liters. And again, technically it's not a standard SI unit, but we're going to use it in chemistry. Our volume will always be in liters. Good question. Other questions? Moving on. What temperature must 0.8 moles of a gas be to occupy 15 liters at 1 atmosphere? So go ahead and work this one through and solve for, what are we solving for here? Temperature. Solve for temperature, I'll be behind you. Plugging in numbers behind you. Looks like we're just about done. If you got a number larger than 100, raise your hand. Good. Larger than 200? Good. Larger than 300? Good. What'd you get? 228 Kelvin. 228 Kelvin. Excellent. So, see if you got a good grasp on this. Now, let's ratchet it up a notch. How many grams of butane are required to fill a 0.1 liter container at 290 Kelvin and 1 atmosphere? This is what we're doing in the lab on Friday. We're going to fill up a container full of butane, and we're going to measure various things. Now, what is this exercise asking? Yeah, it's asking for grams. So we're going to solve for N, do a one-step T-chart, and convert to grams. So go ahead and do your Pivner like usual. Solve for your N, then convert your N to grams using butane's formula of C4H10. And again, you are going to get a small number because, again, if we're at STP, 1 mole is going to occupy 22.4 liters. We're not even anywhere near that. We have 0.1 liters, so we're looking at a very small number of moles. I got 0.0042 moles of butane.
What'd you get?
42 10,000ths of a mole of butane.
That's all you have to do, right? So then do we redo the problem?
Butane has the formula C4H10. We do need to figure out what its molar mass is. What is the molar mass of butane? 58. So if you're unsure where this number comes from, we have 4 times 12 for the C4, and then H10 is 1 times 10. This is 48. This is 10. So put them together, 58 grams per mole. So our butane has a molar mass of 58 grams per mole. My Pivnerd told me, I think I'm right. Did you check my work? Is it 0.0042 moles? Okay. So I multiplied 0.0042 times 58, and how many grams of butane will I need? 0.234. 0.234? 243. How about 24 grams? Let's go ahead and round there. Yeah, well, here we are. So, is this clear? Yeah. Let's complete our exercise. Grams, C4, H10. This is what we're doing on Friday. Yay! We're going to pass mass through a glass in class and then find the mass of the gas that we pass through the glass in class. Yeah. I've had a lot of practice. Okay, one more type. One more type of ideal gas calculation, and that is when you don't know what your gas is and you have to figure it out. So consider this. What is the molar mass in grams per mole of a gas if 0.84 grams occupies 12 liters at 1 atmosphere and 350 Kelvin? So how should we go about solving this? Right, because what it wants to know is the molar mass. So the exercise wants the molar mass, and we know that molar mass is so many grams per 1 mole. So what we're going to do is we're going to come up with a ratio that is going to be 0.84 grams to some numbers of moles. Is anything in the periodic table 0.84 grams per mole? No. But we're going to come up with a ratio. So once we know the number of moles that we get from N, we're going to plug it into this, get the ratio, and that will be our grams per mole. So do your Pivnerd and solve for N. me a thumbs up if you found the number of moles, if you were that far. Okay, give me another 30 seconds before I write it on the board. Now, if I do the end properly, I think my number of moles is 0.42 moles of my unknown gas. All right, so I'm going to take that 0.42 and the 0.84 grams I have and say the molar mass ratio is going to be 0.84 grams to 0.42 moles. Or in other words, what is this ratio in whole numbers? 2. 2 gram per mole. Okay, again, there is nothing that is 0.84 grams, but the ratio still works. So we have a ratio of 0.84 grams to 0.42 moles. That gives us a molar mass of 2 grams per mole. What gas is this? H2. It's the only thing that is 2. What about helium? Helium is 4. Okay? That's Pivnerd. Okay? That's PV equals nRT. So this isn't about gases changing, it's about gases at one particular state, how much pressure, volume, and temperature they exert. Questions? So if there's no questions, you're ready to move on? Let's move on. Okay, Dalton's law, the easiest law there is. Now I'm going to give you the wordy Dalton's law, then I'm going to show you how to use it, and it's really, really, really simple. Sometimes Dalton's law is called Dalton's law of partial pressures. It basically says this. If you know the portion of gases in a sample, then you know the portion of moles, and you know the portion of pressures. So if half of your gas is gas A, and half of your gas is gas B, then gas A is exerting half the number of moles and half the pressure. And gas B is exerting half the number of moles and half the pressure. Or in other words, that. Okay, so that's Dalton's law of partial pressures. Now let me show you what this is actually useful for. Let's pretend, I know we're not even close, but let's pretend that there is 0.5 moles in this balloon. 0.5 moles of air. Now I know, if it was 0.5, what's the actual volume? Anyone remember? Ish. 1 mole is how many liters? 22.4? Okay, remember that? So at STP, which we are not at, but at STP, 1 mole is 22.4 liters. So let's just pretend that there's 0.5 moles of air in here. Okay. Now I know that I learned my gas proportions. How much of the air is oxygen? Yeah, 21% of the air is oxygen. And how much is nitrogen? 78% of the air is nitrogen. And the rest is water vapor, carbon dioxide, argon, helium, whatever. Make sense? So using these relationships, how many moles of oxygen are in my balloon? If there's 0.5 total, how many moles of oxygen are in my balloon? You can do your math. You can do your calculator if you want. Just bang on that calculator for a while. 0.1? Okay. So about 0.1 moles of O2. In other words, 21% of that 0.5 moles is oxygen. And what about nitrogen? About 0.4. About 78% of my 0.5 is nitrogen. So about 0.4 moles of nitrogen. Does that make sense? That's how you use Dalton's law. If you know the proportions of gases in a sample of gas, you just apply that proportion to pressure or moles or whatever. Questions about Dalton's law? Okay. There's your balloon. That's your souvenir balloon full of buyer's breath. Enjoy.
Can I keep it?
You can totally keep it until it pops. Okay. Now this is a great law. Graham's law of gas effusion. We actually already did Graham's law last week. Remember when we were talking about... Now you're missing one pencil. Oh, okay. So remember last week when we talked about temperature? Who remembers what temperature is? There it goes. Who remembers what temperature is?
Let's say, no, 270.
Guys, it's just a blowing up balloon. Relax. The definition of temperature, what is it? Nope, that is standard temperature. But if somebody on the street said, hey, I'll give you $1 if you told me the definition of temperature, what would you say?
I'd say that it's a measure of the air. I can't remember what you said. I know what you said.
We're getting there. It's the movement of particles. It's a measure of something.
Yes. Oh, yes.
It's a measure of the energy of the system. Good. What kind of energy? Kinetic. So temperature is a measure of the average kinetic energy of the particles. So temperature is a measure of the average kinetic energy of the particles. And kinetic energy has a formula. What is that formula? Turn your page one back. 1/2 mv squared. Yeah. So kinetic energy is 1/2 mv squared. So this is the kinetic energy of gas particles, a baseball, a loogie, or a truck. Okay? It's just 1/2 mv squared. 1/2 times mass times velocity squared. Now I said last time we were talking about this, that if you have two samples of gas at the same temperature, they have the same 1/2 mv squared. And the example I used was you have argon at 40 grams per mole, and you have nitrogen at 28 grams per mole. If they are at the same temperature, then they have the same 1/2 mv squared. But nitrogen, because it is smaller, is traveling faster. If you have two samples of gas at the same temperature, the gas that is larger is moving slower. And the gas that is smaller is moving faster because their overall 1/2 mv squared will be equal. Capiche? Okay, so that's Graham's law. It simply states that when you're looking at gas movement, the faster the gas particle is, the larger it's going to, or the smaller it's going to be. Larger gas molecules will be moving slower, and smaller gas molecules will be moving faster. Now, the reason it's called Graham's law of gas effusion is because effusion is different than diffusion. Effusion is the passing of a gas in one direction through an opening. Passing of a gas through one direction in an opening, or through an opening. For instance, if you opened a perfume bottle, then the perfume first must effuse in one direction before it diffuses throughout the room. If you poke a hole in a tire, the air must first effuse in one direction through the tire hole before it diffuses through the room. When you fart, your gas must first effuse in one direction before it diffuses throughout the entire room. Get the idea? Can you see the difference between effusion and diffusion? Go home and tell your parents all about it. Oh, that part is E-fuse, not diffuse. E-fuse somewhere else. Okay, so Graham's law is simply the math behind the principle. That if you have two samples of gas at the same temperature, then they will exert, or they will travel speeds based on their molar mass. So consider this. You just set the 1/2 mv squared of one gas equal to the 1/2 mv squared of another gas. That's Graham's law. That just becomes math. Are you ready to do some examples? Before we do some examples, are there any questions about this principle? Okay. So, most important, big fat gas molecules move slower, little svelte molecules move faster. Red Rover, send the big fat gas molecule over. So, let's do some examples. Oh, before we do some examples, let's talk a little bit. Now, you saw this on your worksheet, but I want to talk about it first. By how much does a gas sample's energy change if its temperature doubles? If you double the temperature, how does that sample of gas, how does the energy carried by that sample of gas change? It goes faster, but by how much? If you double the temperature, what happens to the energy? It doubles the energy. Does it double the speed? No, because speed is v squared. Remember that v stands for velocity, a little v stands for velocity, which is a fancy way of saying speed in one direction. Okay. So if you double temperature, you double the energy, but you don't double the speed, because speed is v squared. Does that even make sense? Good, because if it shows up on the test question, you should all get that one right. By how much does a gas sample's energy change if its speed doubles? Oh. No, it does.
Oh, it does.
If you double speed, how much does the energy change? 4 times. It double squares. So again, since v is v squared, if you double the speed of molecules, you quadruple the amount of energy those molecules are carrying. Okay. If you're driving down the road at 30 miles an hour, and you increase your speed to 60 miles an hour, you've quadrupled your killing speed. Or killing power. Increase my killing power. Okay, here we go. If oxygen is traveling at 450 meters per second, right now, then how fast is nitrogen traveling? Assuming there's the same temperature. So we use our formula, 1/2 mv squared. I'm going to put oxygen on this side, O2, and I'm going to put nitrogen on this side, N2. Meters per second. Okay, there's all the information that we have. How can I fill in the molar mass for oxygen? Where would I get this number? Direct table. And what is oxygen's molar mass? 32. 16 times Q. 32 gram per mole. And nitrogen's, what's nitrogen's molar mass? 28. 14 times Q. Okay. All right. So there you go. So now what you need to do is solve of nitrogen. And again, when you get your answer, see if it makes sense. Nitrogen is smaller than oxygen, therefore it should be moving what? Faster. Good. Again, the number you get for V should be larger than that of oxygen because nitrogen is smaller. And again, the trickiest thing about these is the square root. A lot of people have trouble with square roots. They forget to do the square root. And they get some number that's ridiculous. Give me a thumbs up if you have an answer you're happy with.
Okay.
Okay. Some people are still calculating. Give you another 10 seconds to finish calculating.
Teachers and students, pardon the interruption. We have an AED drill over by the band room. All first responders, please go to the band room for an AED drill. Thank you.
No, thank you. Okay, so if you got a number that is larger than 200, raise your hand. Larger than 300. Larger than 400. Larger than 500. Good, what'd you get? 481 meter per second. So in other words, we're saying because two gases are the same temperature, they have the same 1/2 mv squared. Oxygen is heavier at 32, traveling at 450. Nitrogen is lighter at 28, traveling at 480. Questions about this? Okay. How fast is argon moving? How fast is argon moving? The 1%, the slightly less than 1% of the air that's argon, how fast is that moving? I would replace our calculation in here with argon's 40 gram per mole, and then solve for argon. And again, argon is larger than oxygen, should be moving slower. should be in the neighborhood of what we have for oxygen, but should be smaller because argon be larger. Argon be a larger molecule. Argon. I love the pirate's booty. It's all gone. I'll get home and the pirate's booty will be gone. I'll have to go to Costco and purchase some more pirate's booty. Then I'll say, not gone anymore. Okay, if you got a number larger than 100, raise your hand. Larger than 200. Larger than 300. Larger than 400. Larger than 500. Good, what'd you get? 402. Excellent. Okay, so 402, argon is larger, so it should be moving slower. Now, this is the last type of exercise we're going to learn, and it's kind of the trickiest, but it's also kind of neat. Consider this. If an unknown gas is moving 3 times slower than that of oxygen, what must be its molar mass? Interesting. So we're going to write our formula down. 1/2 mv squared equals 1/2 mv squared. Have you guys realized that you can usually just cancel out the 1/2? Some of you are into that. Okay. So we're going to make this the oxygen side, and we're going to make this the unknown gas side. What's oxygen's molar mass? 32. How fast is oxygen moving? You want it to be 450? I mean, we can make it 450, but the great thing about this is we can make it anything we want.
5.
0? No, we can't make it go 0. 5. 10? 10. We'll make it 10.
7. Break even.
10 squared. Okay. So the unknown gas is what we're looking for. We want to know what it is. Now, if oxygen's moving at 10, how fast is the unknown gas moving?
30.
How much?
Oh, 3 times slower.
3 times slower. So
That's a bad number.
So like
3.33333. Okay. 3.3 repeating for you math folks. Squared. Now you can solve for the mass of the unknown gas. Kind of like what we're doing on Friday. We're going to pass mass. We're going to pass a mass of gas through a glass in class. Then we will find the mass of the gas that we pass through the glass in class. Don't get knocked on your ass. Was that just too crass? Don't give me any sass. When you get an answer, ask yourself, it's moving 9 times slower, or sorry, moving 3 times slower, so it should have 9 times the mass. Is your answer 9 times more massive than oxygen? Again, if they're at the same temperature, and the unknown gas is moving 3 times slower, in order for it to have the same energy, it has to have 9 times the mass. How massive is my unknown gas? 288 grams per mole, which I think is 32 times 9. Sound about right? All right. One last thing. It's probably not any of these gases. It's probably one of big, fat, huge gas that's all multiple molecules or multiple atoms. Okay. So, are we cool here? Okay. One more principle that I want to talk about, and it's a principle we're going to revisit when we talk about something called colligative properties. Talk about vapor pressure. Vapor pressure is the pressure a liquid exerts by trying to force its gas molecules into the gas phase. This is the pressure that my toddler exerts on the gate when he wants to get out of somewhere. Like, I'm not where I want to be. I want to be on that side of the gate. He's pushing on the gate. Water molecules, liquid molecules do the same thing. They say, I don't want to be a liquid anymore. I want to be a gas. So they exert a vapor pressure into the atmosphere. So this is how this works. Gas forms above a liquid and exerts a pressure. We're going to revisit this later on next week too. Higher temperatures mean the molecule is moving faster, therefore exerting a greater vapor pressure. I'll show you a really cool example of this next week when we do the clouds in a bottle activity. So the warmer the gas molecules are, the faster they're moving. And the molecules that are moving faster will exert a greater vapor pressure. This is like my toddler kind of ramming himself against the gate, running and getting a head start. Eventually he's going to break right through. Eventually he's going to have so much energy he's going to bust right through the gate and get to where he wants to be. Molecules do the same thing. If a molecule gets so warm that its vapor pressure is larger than the atmospheric pressure pushing down on it, what does the liquid do?
Oh, no.
Exactly, yeah. That's exactly right. So if a liquid is warmed up to the point where its vapor pressure is larger than the atmospheric pressure pushing down, the atmospheric pressure says, no, you stay as a liquid. And the liquid says, I want to be a gas. No, you stay as a liquid. I want to be a gas. No, okay, well, I'll get really, really warm. If my vapor pressure exceeds the atmospheric pressure, then it what? Starts with a B and ends in oils. It boils, okay? So that's what happens. When a vapor pressure is larger than the atmospheric pressure, it boils. And I will show you what that looks like next week. I will boil some water